going. So again, very quickly, I want to review a little bit of the information theory concepts that we did. Just say concepts, just to be respectful of that subject is very deep. So we saw the idea of the entropy in the last lecture, and a classical example that you can conceive of to get insight into entropy is this idea that, let's say I have some set of events that I'm modeling, right? So maybe event A, event B, event C, event D. Let's say event A has 25% probability of happening. This is 12.5%. This is 12.5%. And this is, say, 50%, right? So let's say this is the probability of these events happening. And maybe think of these as weather situations, D being driving conditions like this, right? And let's say you're a weather station, and the weather station can send you bits of information. It can send you either a 1 or a 0. And so what is the least amount of information that can be conveyed to you that contains, exact messages? Okay, so that's the idea. By the way, everyone is on Zoom. All right. So I think there are many ways of doing this. I would say the most logical one to do this is immediately look at the highest probability event and ask. So we want to get there with ones and zeros, right? And ones and zeros can be thought of as yes and no kind of thing. So your question is, if the first question is it D? That's a question. The answer is yes, and we get to D, right? If it's not D, then it is B, C. Then you ask the next question. You ask, is it A? Okay. If it's A, then you get to A, right? If not, you ask, is it B? And if the answer to that question is yes, then you have B. If it's no, you have C, right? So the very simple way of coding this or sending signals is by saying, okay, I want to assign this a code of 1, and I want to assign this a code of 0, 1, because this was already a 1, and that's a no, and that no is a 0, and then the yes is a 1. And this would be a 0, 0, 1, and this would be a 0, 0, 0. Okay. So in other words, if the weather station is telling you, or if it's giving you this information that C is going to happen, it is going to send you a code 0, 0, 0. Okay. And this kind of coding in this case, or signal that is sent to you, is optimal because, first of all, this kind of coding is optimal. And the reason is, so what is the average number of bits that you expect to receive in this scenario? Let's wake everyone up here. So what's the average number of bits you expect to receive? How do you compute that? Yeah.
Probability of each outcome by the number of bits.
Yeah. So it's 0.25. Okay. So the probability of D is 0.5, right? 0.5 into 1 bit plus probability of A is 0.25. 0.25 into 2 bits plus 0.125 into 3 bits, and that happens twice, right? So this is 1 plus what is 6 into 0.125? 0.75, right? So that's basically 1.75 bits. Okay, so this is the average information you can expect from, in this case, the weather station, right, is 1.75 bits. And if you compute the entropy of this distribution, if you do summation of pi log 2, 1 over pi, you will also get 1.75 bits. So this is H on the entropy, right? So the entropy is the average amount of information you expect. And as I said, so like in this case, it's optimal because again, these things match up. But if you had assigned a different code, for instance, instead of let's say you use the standard, you have 4 possibilities, right? So one way of coding, so by the way, this is called Huffman coding. And you basically, the codes were for each of those 0, 1, 0, 0, 1, 0, 0, 0, and 1. Okay, so this is Huffman coding for this. So typically, I mean, if you use some other coding to represent this distribution, you would get something that's larger than the average amount of information you expect to get, because your coding is completely in tune with the underlying probability distribution. Okay, so that's the concept we saw last time. And we also saw last time what a bit was and why is it a log 2, right? I said 2 to the power minus k is what it was. So anyways, you can look at the last lecture for a little more information. But I wanted to see if there is anything that I need to explain about this. Is there any more questions on this? This is what we did. Yeah, go ahead.
There's only 4 outcomes. Is there a reason why we can't represent this with only 2 bits for every sort of state? Like, I'm not entirely sure why.
If you do 2 bits for each, what do you have? 0.5 into 2 is 1, and then 0.25 into 2, then 0.125 into 3 into 2, what would that be?
It'll be 2.
Sorry?
It'll just be 2.
It'll be 2?
Yeah.
Yeah, so it'll be more. It'll be less. Yeah, so you basically, the idea here is very logical, right? For the most probable outcome, you're assigning the least amount of bits so that the average amount of information that you send is optimal. Okay. But typically this is not a class in EE, so we don't usually think in terms of bits, but I'm gonna relate that to something very physical, like the amount of information you get from an experiment, etc. Okay. But fundamentally, this idea of log 1 over P of I, right? P of I is the probability of that particular outcome I, is called self-information. It is basically, if you want to give a good interpretation of this, it is the information that you have acquired upon being told. I'm being a little bit loose here, but I think you get the idea. Right? Initially, you had no idea of which of those possibilities is going to happen. And then if somebody told you possibility I has happened, then log of 1 over pi gives you is basically the amount of information you gain, right? So think about it as an observation. You're running an experiment to measure something, and before running that experiment, you don't know what that value is, but you may know probability distribution. But that particular value has been observed. So how much information have you gotten? So that's the idea. And so the entropy is just the expected information. It's the average over the whole thing. So if you do a large number of experiments, how much information do you get from that process? And similarly, we also saw cross entropy. This is nothing but summation pi log 1 over 2i. Okay? So again, you can relate it to the optimal coding, right? So there was a question in class that what if we assign 2 bits to each outcome? If you do that, then basically qi would be 0.25, right? So if you're assigning the same amount of bits to each outcome, then you're assuming effectively that all those probabilities are the same, right? So if you're assigning 2 bits, then the effective distribution that you're representing would be, probability distribution where everything is 0.25, in which case you have the cross entropy. Okay. So, yeah.
If just I don't know if this problem was instead of discrete continuous, you think the idea that he said had of the 2 bits could still be the optimal?
If the problem is continuous, in what sense? If the underlying distribution is continuous?
Yeah, so
so you're opening a Pandora's box here. So a lot of these statements, when we talk in discrete variables, they're very rock solid.
Yeah.
When you go to continuous, it becomes a little less definite. We'll get to that. And in fact, when you go to continuous probability distributions, entropy can even be negative. And there are some other, some weird things that happen in measure. But in any case, as with many things, we derive inspiration from this and then we adapt it to our problems. So anyway, so the cross entropy is really, it's kind of trying to measure it's basically measuring some kind of excess bits, okay? So, if you want to assign the same kind of English definition to cross entropy, then you can say cross entropy is nothing but the average message length when the code is transmitting information assuming a distribution Q, whereas the true underlying distribution is P. Okay. And the difference between the two is the KL divergence. So KL divergence, again, different ways in which this is represented. I'll just use KL Q, basically h of Q minus h of P. Okay? So KL divergence is really the excess bits. In a sense, it's the penalty you pay for using the suboptimal distribution. Okay.
Or could you provide an example for like the P and Q case? Because why would you want to be transmitting information from Q if you have P?
Okay, sometimes you may not, sometimes your coding capacity may not match with the underlying distribution. So I conveniently used this, I conveniently used 25, 12.5, 12.550, right? So those are all like fractions of 2, right? 1 by 4, 1 by 8, 1 by 2. But if I change that to like say 0.43 and 0.31 and whatever, then the underlying entropy would be some number, and whatever this kind of coding if you use, it will be suboptimal for that. Not because you don't know the underlying distribution, because your coding method, your vocabulary is restricted.
Okay.
So it can be suboptimal for various reasons.
Okay.
But there are other ways you can fix that, right? So again, there are two things happening here. So one is you are representing a code, and that is optimal for a particular distribution, etc. And in many cases in real life, you may not know P, right? So that is that. Okay, so yeah, so entropy, cross entropy, and KL divergence. KL divergence is the excess bits, right? Is a Kullback Liebler divergence. So in this particular case, it measures excess bits. In the general case, KL divergence is nothing but you can think of it as a distance between two distributions. That is what it is, okay? And again, but you have to be a little bit careful. And let's write the KL divergence, and the H of PQ is summation I PI log yeah. So this is the definition, not H, sorry. So the KL divergence, the actual definition is this. And there is also something called the reverse KL, in which case you use QI here. And this is not symmetric, right? KL divergence between P and Q will not be the same as the distance between Q and P. So in that sense, it's not like a metric distance you're used to, but it's very convenient to think about this as a difference between two distributions. Or if you, in the discrete case, especially if you're in the binary setting, then it's basically excess bits. That's what it is. And very many times, as we move towards the later part of the lecture, later part of the course, and we start looking at statistical learning theory, the scale divergence and cross entropy will come back over and over again for very particular reasons, which we'll get to later. And it's very convenient to have. All right, so now probably the even more important concept that we want to introduce is, before we talk about mutual information, let's talk about conditional entropy. right? So let's say you have two random variables, x and y, and x and y have their own distributions. For now, let's assume they are discrete, right? But the same ideas transfer to the continuous case. So, you know what h of x is, right? It's the average uncertainty in x, or the average amount of information you expect, depending on which viewpoint you take. So we know what h of x is. So you just write it, average uncertainty associated with random variable x, right? Or average amount of information you gain if you are basically observing actual realizations of x, whichever way you want to take it. And so the same idea, h of x given y is average uncertainty I would say remaining in your knowledge of x given y has been observed. This is h of x given y, and you can see that in a Venn diagram. Well, I don't want to draw that. Right, let's say you had, so this is h of x, this is amount of, so this is amount of uncertainty in x, and then this is some other random variable, h of y, and this part, the remaining uncertainty, this remaining uncertainty is h of x given y. And as I mentioned a couple of lectures ago, doing physics or doing predictive modeling is about conditional distributions, right? So unconditional distributions are maybe useful in some settings, but it is always conditional distributions that matter, right? So I know my initial condition predict me the solution at some future time, or I know the pressure, get me the velocity or whatever it is, right? So conditional distributions are very important. So mutual information is basically that particular uncertainty reduction. So let me color that. So this would be mutual information. So the way you want to define this is, so this is the average amount of information that you gain about one distribution if you know the other. Okay, so I of x, and this is symmetric. Okay, so I of x semicolon y is I of y semicolon x. So it's basically this intersection, and it's a very important quantity, as we'll see in the next 50 minutes. So this is really the the mutual information the average information gained by the knowledge of one random variable with respect to another. And that's a symmetric function. And if you want to write it as an identity, then so I of x, y is h of x minus h of x given y, which is the same as h of y. Let me y minus h of y given x, and this is the same as I of yx. And one nice thing is, even so, when you have continuous probability distributions like the Gaussian, this h can go negative. Okay, so any of those entropies can go negative, but this quantity always stays positive, regardless of whether you have continuous or discrete or whatever. So it's, in that sense, it's a little more definite. So any questions on the mutual information? Yeah.
Probably not that related to mutual information, but you just mentioned that the entropy can go negative, right?
Yeah.
For a continuous distribution.
Yeah.
For example, Gaussian. What does it mean?
Well, what does it mean?
Yeah, for a negative.
Yeah. So that's the thing. So well, it is with respect to some reference. That's it. In the discrete case, especially in the binary case, when you say information of 0, right? Then you're basically not getting any information, right? And everything is with respect to that base of 0. But in continuous distributions, that is not the case. So you can't literally interpret. This is still true. H of y will always be greater than h of y given x, and h of x will always be greater than h of x given y. But it's that lack of a clean reference, and the measure, if you look at it from probability measure standpoint, also there is some weirdness. Differential entropy is not to be taken as literally as discrete entropy. Yeah, but it's really a reference issue. Okay, so but again, if we write if we can write mutual information in this form, which is good, but we can also write it in a more intuitive form, in my opinion. So you can write I of x, y as scale divergence of p x, y given p px, py. Okay. So you can write it like this. So the mutual information is the difference between the joint distribution of x and y and their products. Okay, so that should give you some insight also, right? If these variables were not correlated at all, then pxy is px, py, so you get mutual information of 0. So obviously that Venn diagram doesn't intersect, there is no intersection. If x and y are independent, one does not supply any information about the other. Okay, but this is also very useful from quite intuitive from a coding standpoint, right? So if you assumed, so if you assumed a coding distribution for px, you'll get a certain code, like what we did earlier, right? If you assume the coding distribution for py, you'll get a certain code, okay? And if you sum them up, you have the full length of the code. But that is if you knew, okay, let me put it this way. So let's say you knew pxy, let's say you know the joint distribution, right? Then you can design an optimal code for that joint distribution, and the average length of that code basically would be the entropy of the joint distribution. But if you don't use the fact that x and y are dependent and you write separate codes for x and y, that will be suboptimal, okay? And so in that sense, you can think about I of x comma y as measuring the excess bits of writing a code assuming x and y are independent distributions versus the actual code length. So again, for the previous case, we computed 1.75 bits, right? So you assume if you knew the joint distribution and designed an optimal code for the joint distribution, you're going to have a certain number of bits. If you don't assume that you know the joint distribution, then your code would be how much ever the length of the code was for px plus how much ever the length of the code was for py. So the excess basically gives you visual information. Okay. Yeah.
So by definition, the joint distribution gives the optimal code.
Yes.
So, okay.
Yeah.
Based on that, I guess the KL divergence tells you if the code is ideal with respect to the.
Yeah.
Okay.
In a sense, this is the true distribution, and this is your suboptimal distribution. But, so anyway, this is from a purely coding standpoint, so it's still excess bits. But now let's think like physicists or engineers. Again, the same thing, it's very easy to see. You can also write this as in the following way. This is expectation of y, expectation over y dkl. So this is more, or different ways in which people write KL distribution, and I don't want to get caught up. So KL of probability of x given y, probability x. Okay. You can also write this as expectation over y, average KL. I mean, these are all equivalent. Okay, so I gave you the expression for what the KL is, right, in terms of two distributions, right? You know what an expectation is. Anyway, so the expression carries over. So this is another way of writing it, and to me, this is much more intuitive. Okay, so let's think about it in an experimental setting. Okay, so let's say I'm running an experiment to infer a parameter, right? Parameter could be viscosity or I don't know, whatever, angle of attack or lift or whatever it is in your problem, right? So that's the observation is lift or drag, and your parameter is say viscosity, right? Something like that. So let's make it more definite. I'm going to run an experiment, and if I run that experiment, I get some data D, okay? And I want to use that data D to infer a parameter, right? A parameter could be, say, viscosity or something like that. Or let's make it even simpler. I go to the wind tunnel and I measure lift, and I want to know what the angle of attack is, right? So let's consider an experiment. Consider a set of experiments, because all of this is averages. set of experiments in which you measure some data, D, okay? And use those measurements to calibrate some parameter theta, right? I think, yeah. So the mutual information between D and theta would be expectation over D, all of the data you took, KL divergence of probability of observing the data, so observing the parameter given the data, and the probability of so this is the mutual information between the observations and your parameters, right? You're measuring D and you want to like calibrate or infer theta, right? And this hits up very nicely, right? So P of theta is so this is your prior belief on theta. So this is before you ran the experiment. This is your understanding of theta, right? You don't know what theta is, but maybe you can guess what it is. So it's the prior belief. Probability of theta given D, as you did in your homework, is posterior probability after you measured something. This is what you think theta is. So you've actually gained some information. Okay. So the KL divergence then measures how much information you've gained given you've observed something. Okay. So if I want to be a little more strict, I would call this as small d, because it's a realization of the big D. But anyway, I think it's okay. Right. So this is the amount of information you gain about theta from, say, a single measurement. And then if you average over all of the measurements, all possible measurements, this is the average amount of information you gain. So in some sense, it is called, mutual information is also called the expected information gain. Okay, so this is the amount of information you gained after a single measurement, and this is the expectation. Yeah.
So if you had different data,
Yeah.
like left, drag,
Yeah.
so you could pick which would calibrate theta the best.
Yeah, you could. I mean, technically speaking, yeah. Actually, you're right. So that's a very good thing. So this is just between two variables, right? You have one parameter to calibrate and you're measuring one thing, okay? But you could have many things, in which case your Venn diagram would be something like this. So there'll be many other mutual informations. There'll be conditional mutual information. This would be like some conditional mutual information or something. And in fact, Sahil has a paper from a few years ago where he basically explores that. You can use that to quantify some identifiability things and many other things. You're right. So I don't want you to think it is always between two variables. You can have any number of variables, and maybe you can group some variables into this. Maybe this is one variable, this is two variables, and this is a million variables. But yes, you can look at that.
But this is not like normalized, so how do you know what is like the right amount of?
Again, this normalization thing is very important. If you're in binary, if you're in discrete, then very clearly everything is in bits. Everything is in bits. So it is very quantifiable, normalizable, relatable. But yeah, if you're in continuous distributions, you get nats, and that's kind of open to interpretation. But as engineers, we would always normalize by something, by some reference that we have confidence in. Okay. So anyway, so this is important. So mutual information is also expected information gain. And later in the course, maybe when we do statistical learning theory, we can actually show that if you take this kind of viewpoint and you add one more variable here and you minimize this whole thing, you basically get the Bayesian. The Bayes rule actually pops out of Bayesian inference is a special case of a minimization of this. So it's in that sense, it's a little more fundamental. But yeah, we'll wait for that later. But this is a very good, again, codes, bits, coding information, especially when you view it in bits. It's very definite, it gives you some insight. But if you want to relate it to something that you some are familiar with, more relevant to this class, viewing it this way is the right thing. And you can and any of these you can write. You can write in the right way. Okay. All right, let's take a short break and then let's start our journey of Boltzmann. Let's take a 3-minute break or so.